Welcome back to Basic Electronics. In this session, we will simulate an op-amp filter and plot the magnitude of the transfer function versus frequency. It is a good idea for you to repeat the steps shown here on your computer. Stop the video whenever required and make sure that you get the same result as that shown on the screen. Okay, let us begin. Let us consider this filter problem. Shown in the figure is a second order KRC filter. It's also called Sallen-Key, and this specific filter is a low pass filter. It's called KRC because it consists of RC components, and this is the K or gain block. Alright, now assuming R1 equal to R2 equal to R, these two resistances being equal, and C1 equal to C2 equal to C, C1 equal to C2. Design the filter for a passband gain of 2 and a cutoff frequency of 1 kHz. Simulate the filter and plot its frequency response. In particular, we will check that it is a second order filter with a cutoff frequency of 1 kHz. And finally, apply an input voltage Vs equal to Vm1 sin omega 1t plus Vm2 sin omega 2t. So these are two sinusoids. One of them has a low frequency 200 Hz, which is smaller than the cutoff frequency. The other sinusoid has a higher frequency 10 kHz, which is higher than the cutoff frequency. So apply this input voltage to the filter, that is when we do circuit simulation, and verify its operation. So what we should see is that the high frequency component is filtered out, and at the output we get only the low frequency component of Vs. And this is our transfer function which we have seen earlier, and in this expression this K here and here is equal to 1 plus RB over RA, and that is the gain of this amplifier section. That is a non-inverting amplifier, as we can see. Alright, now let us put R1 equal to R2 equal to R and C1 equal to C2 equal to C, and with that H of S reduces to K divided by 1 plus 3 minus K times RC times S plus RC squared S squared. At low frequencies we can ignore the terms in S and S squared because omega is small, and therefore H of S becomes simply equal to K. So when we say we want our passband gain equal to 2, what we are really requiring is that K should be equal to 2. So that is our specification, and let RA be 10K, then we have 1 plus RB over RA equal to 2, which means RB and RA must be equal, so therefore we get RB equal to 10K. And note that this 10K is not very critical. We could have picked 5K or 20K, for example. Okay, our cutoff frequency should be 1 kHz, and for this circuit omega C is given by 1 over RC. That should be 2 pi times 1 kHz. Let us pick C to be 10 nanofarads, and that gives us R of about 16 kilo ohms. Let us now come to the second part of the problem, in which we have these two sinusoidal voltage sources, Vs1 equal to Vm1 sin omega 1t with a low frequency, and Vs2 equal to Vm2 sin omega 2t with a high frequency. We want to add these two and then apply to the filter circuit, this one. And we can use our op-amp summer to add these two voltages, and that is what is shown over here. So Vs is given by minus Rf over R1 prime times Vs1 plus Rf by R2 prime times Vs2, and we can choose all of these resistances to be equal, say 10K, and then we get Vs1 plus Vs2. This minus sign is not really important in this problem. Let us prepare the circuit schematic first, and we begin by getting the components that we require. Let's say we use the 741 op amp, then the resistor, capacitor, and ground. We can also take the connector element, which could be useful. Alright. Okay. So here is the circuit that we want to make, the filter. And we notice that our op amp needs to be flipped. So we select it and then go to flip and then flip vertically. Now we have plus minus here as we would like. Let us place the connectors so that it will help us in wiring. We need one here, one here, let us place the resistances, one there. Let us do Control C, Control V. We need one here, one here, and this needs to be rotated like that. And we also need one here. Okay, we can move some of these things a little bit like that. We need one more capacitor, so let us do Control C, Control V, and this needs to be rotated, and we can connect the ground over there like that. Okay, we also need a connector here. We can move these a bit. Okay. Before we do the wiring, we need to get two more components. So let us go to the panels menu, get our toolbox back. We need VSRC AC. We also need ground dummy. Alright. We don't need this connector. Let's remove it. Okay, we can now start the wiring because all the components have been placed. Alright. The next step is to assign values to the components. This should be 16K. This is also 16K. 10 nano. Also 10 nano. And this one is 10K. And so is this. We can display these like that. Let us now assign the amplitude for this voltage source. Let us make that 10 millivolts. And frequency does not really matter because we are going to vary it anyway. Okay. Now let us name these nodes, the input node and the output node. That is our in and that is our out. And let us define output variables, the input voltage and the output voltage. And we want to make these AC quantities, that is phasor quantities. So we right click and then select AC. And you notice that it becomes node V AC of in. In is the node name. Similarly for the output node. Okay. We can change these names. Alright. Before we prepare the solve blocks, let us look at the help file for this op-amp. And we notice that it has got transistors and some other components. And because of that, we first need to perform a DC simulation for this circuit so that an appropriate small signal model is prepared for the op-amp, and then follow it up with an AC solve block. So let us do that. Go to solve blocks, add solve blocks. So this is the first DC solve block that we would like. Let's add one more, and that should be an AC solve block, like that. Next, we need to get the vary frequency statement in the AC solve block. So let us look for that statement, drag it, and then click on it. And now we see a bunch of parameters. The vary type should be logarithmic because our frequency is going to vary over a wide range. Number of points should be reasonably large so that we get a good resolution. The actual frequency values, or the range of frequencies, is specified in this field here. Let us go from 5 Hertz to 50 kilohertz, and that is indicated by 5, 50 K. And notice that as we type here, this sentence in the AC solve block also gets constructed. Next, let us get the output block statement. And let us select the output variables now. And we note that because our VIAC and VOAC are phasors, the program has made both the phase and the magnitude of these quantities available to us for plotting. In this case, we are only interested in the magnitude of the output voltage, so we will pick mag of VOAC, like that. Okay, we can now run the simulation. Let us pick the frequency as the x-axis and the magnitude of the output voltage on the y-axis. And in this case, we need to use logarithmic axis because of the wide variations both in x and y. So that is what our plot looks like. So at low frequencies, the magnitude is 0.02, which is what we would expect because our input amplitude is 10 millivolts or 0.01, and the gain is 2, so that is 0.02. Also note that this slope should be 40 dB per decade. That is, as we go 1 decade in frequency, we should go about 2 decades in the output magnitude, and that is indeed happening. So this filter does seem to perform as we would expect. What about the cutoff frequency? We expect it to be 1 kilohertz, so these two asymptotes should meet at 1 kilohertz, and that also seems to be happening. Let us come to the second part now, in which we want to perform a time domain simulation with an input voltage which is a sum of two sinusoids, Vm1 sin omega 1t, Vm2 sin omega 2t. The first one has an amplitude of 0.5 volts and frequency 200 Hz. The second has an amplitude of 0.1 volts and frequency 10 kilohertz. So we need to construct this op-amp summer first, and then apply two input voltages here, and then drive the filter, this circuit. Alright. So let us edit our earlier circuit, the filter. We're going to have an op-amp summer here. We can remove the source. And let us first get the components that we require for the op-amp summer. Resistors. This is going to be our RF, that is R1 prime, that is R2 prime. We also need two sinusoidal sources, voltage sources, and we also need dummy grounds. Like that. Okay, let us now start the wiring, but we will get some connector elements. Place one there, place one here, place one here. Alright, we can now start the wiring. Okay. Let us assign the component values now. All of these resistances are equal 10K. One of these sources has got an amplitude of 0.5 volts and a frequency of 200 Hertz, and the other has an amplitude of 0.1 and frequency 10 kilohertz, like that. Let us display the component values now. Right click, add default property text boxes. And let us also display the amplitude and frequency for the sources. So the way to do that is to right click anywhere on the canvas and then select add element property text box, and then select the source that we want, like that. A is the amplitude, so click on A, say OK, then A comes over here. Do that again and select F Hertz, frequency in Hertz, and now we have both of those. Okay, let's repeat that for the second source. Like that. Let us name these nodes. We can call this S1, source 1. We can call this S2. We can call this S. That is the output of the op-amp summer. And let us also display these node names. The way to do that is to right click on an element node which is connected to that wire and select add node name text box, and the name appears over there. So that is our S1, that is S2, and that is S, like that. Our next step is to define output variables. So click on output variables, and we can click on add variable while pressing down the control key. That way we can select more than one output variables. Let us select S1, S2, S, and the output. Alright, let us rename these. Like that. Before going to the solve block section, let us figure out the simulation interval. We have two sources. This has a frequency of 200 Hertz and this has a frequency of 10 kilohertz. So the larger time period is given by 1 over 200, and that is 5 milliseconds. And suppose we decide to simulate for 4 of these cycles. That means our simulation interval would be 20 milliseconds. Alright, let us now go to the solve blocks. We can remove these old ones which came from the filter example. Add a new solve block, and we should change that to transient simulation, like that. One comment about the numerical method here. We are going to simulate a filter circuit, and in these circuits the artificial damping that is introduced by the backward Euler method can sometimes cause a problem with accuracy, and therefore what we should really use is the trapezoidal method. So let us remove that backward Euler option and bring in trapezoidal rule. Like that. As we discussed earlier, our t end could be 20 milliseconds. What about the simulation interval, delta t? That should be determined by the source with the higher frequency, and that is 10 kilohertz. Now 10 kilohertz corresponds to a time period of 0.1 millisecond or 100 microseconds, and our delta t should be small compared to 100 microseconds. So we can choose, for example, 1 microsecond. Our next step is to bring in the output block statement, and we need to select the output variables now. We will choose VS1, VS2, VS and Vout. These were defined for the AC simulation earlier for the filter example, and we don't need to look at them now. So say OK, like that. Let us now run the simulation. And let us first look at VS1, VS2 and VS as a function of time to make sure that our op-amp summer is indeed adding VS1 and VS2. Alright, so that is what the graph looks like. Let us expand a little bit. Okay, so here is our VS1, the low frequency input voltage. This is VS2, the high frequency input voltage, and this is our VS, the output of the op-amp summer. So notice that this high frequency voltage has got superimposed on the low frequency input voltage, giving us VS. And note also that VS has got inverted because our op-amp summer is an inverting summer. Okay, now let us look at VS and Vout together, and from these two we should be able to make out the filtering action of our low pass filter. It should filter the high frequency component because its frequency is much higher than the cutoff frequency, which is 1 kilohertz, and it should retain the low frequency component. So let us plot these two together, and that is what we get. Okay, let us expand maybe 1 or 2 cycles. So this is our input to the filter, and that is the output of the filter. So notice that the high frequency component of the input voltage has got filtered out, leaving only the low frequency component. And the amplitude of the filter output is higher than the input voltage because our filter has a gain of 2. Here is the plot along with the circuit diagram. The blue graph is VS and the red one is Vout. And as we have commented earlier, the filtering action can be very clearly observed from these graphs. Note that there is a small phase difference between the low frequency component of the input and our actual output voltage. But in most applications, this phase difference is really of no particular consequence. To conclude, we have simulated an op-amp filter from scratch, and hopefully you have also got that to work on your computer. In the next class, we will look at a few other op-amp circuits. Until then, goodbye.